We're now ready to look at how to improve both the steady state error and the transient response for a given system using cascade compensation. And so it turns out we don't have any new fancy technique, but rather what we're going to do is just improve both of those qualities independently using the techniques we've already talked about previously. And so what that means is we're going to have two general approaches or two options as we're solving these types of problems. Our first option is we can start by designing for our given transient response. So we can design for a transient response improvement. So maybe we want to decrease our settling time or our peak time by some percentage. And then once we've done that, we can design for our desired steady state error. So design for our error in the steady state. So maybe we want to increase the system type or maybe just decrease the finite error by some amount. Our second option is of course just going to be swapping the order. So we could instead start by designing for our steady state error. And then once we've done that, we can come back and we can design for our desired transient response. So desired transient response. And ultimately, it's not going to make a huge difference which of these two methods we use. However, in the textbook, they consider method one, and therefore that's what I'm going to consider in the lecture notes as well as in these videos. So that means we're going to start by designing for the desired transient response, and after we've done that, we're going to go back and design for our steady state error. Now, it's worth mentioning that regardless of which two of these options we're using, we need to be aware that our second design phase can alter the results that we designed in the first phase. So our second design phase can slightly alter. So it's typically not going to be changing it greatly, but we do need to be aware that it's not going to stay consistent. So what was designed in our first design phase. And so what we're going to see is that's not necessarily always a bad thing. Sometimes it works in our favor. So in this case, because we're looking at method one up here, what that means is we're going to start by designing for our transient response. And let's say maybe we designed it so that our TS was initially 3 seconds, and we made our TS with the compensated system go down to 1 second. Well, when we come back and we do this second design phase, maybe now we wanted to decrease our steady state error. So maybe we had some steady state error that was finite at 0.8, and we wanted to decrease that to a value of 0, so increase our system type. So maybe in doing so, we no longer have this settling time of 1 second. Maybe we have a settling time of 0.8 seconds. Or maybe it's a settling time of 2 seconds. So the exact change we can't say without knowing the details of the system. However, it is always going to be slightly altered as we go through that second design phase. So just be aware of that. And again, that's true whether we're using method one or method two up here above. So we also have sort of two general approaches in terms of how we're setting up these systems. So in addition to sort of our two options we already talked about, we also have two other options in terms of whether we're going to use our PD and PI or our lag and our lead. So two general approaches. So our first of these two general approaches is going to be to combine our PD and our PI. So combine PD and PI, so those are ideal derivative and ideal integrator. Controllers. And so what that's going to give us is our PID controller. And so that is probably something you've heard before or seen. We've seen it, I think, at least in one homework problem sort of leading up to this. And so, of course, what that stands for is now we're going to have a proportional part of the error signal fed forward plus an integral part of the error signal plus a derivative part. And so we'll see that in a block diagram in the next video. But of course, that's a mouthful, so instead we'll usually just call that a PID controller. And as I've said multiple times, because we have this PD and this PI, our ideal derivation and our ideal integration, that means we're going to be using active components. So our active components are our op amps, and that means that it's going to be a little more expensive to implement, but in most cases that's going to mean we have more accuracy. So again, we always have these trade-offs. The second option is, of course, instead of using our PD and our PI controllers, is we can combine a lag and lead controller. So combine lag and lead compensators. And so what that's going to give us is something called a lag lead compensator. And so due to our limited time, we're not going to look at an example of our lag lead compensator. We're going to focus on the PID because that's something that is a little more commonly used. But again, let's note the main difference here between our lag and lead compensator and our PID compensator is that the former is implemented using passive components. So this is going to be resistors, capacitors, and inductors. So we don't have any op-amps in these circuits. And as I've said a few times as well, if you do want to see what these circuits physically look like, you can look in section 9.6 in the textbook.